Hi there, it's Mrs. Tollison with your review video for our Introduction to Matter, Energy and Chemical Reactions, and Density tests that's coming up. As always, I encourage you to get your notebook or your study guide, have a pen and paper ready. There are some practice problems in this review video, so it's really good if you have a pencil and paper so you can pause the video and do the practice. So you can watch this video as many times as you want, and if you have any questions, come see me. We started off by reviewing a little bit about the 5th grade standards and talking about what is matter and what it's made up of. And basically the general kind of understanding of matter, the most basic thing is that everything, whether it's living or not, is made up of matter. All matter is made up of atoms, and then those atoms make up different elements. Elements are the simplest form of matter, and they're made up of only one kind of atom. We're not getting into the whole periodic table. We've talked about it briefly, but just that each element on that periodic table has its own unique properties and characteristics. Atoms are made up of 3 smaller parts called protons, electrons, and neutrons. Almost all elements have neutrons, but there's at least one, hydrogen, that does not. There are 4 states of matter, but we only talk usually about 3 of them, solid, liquid, and gas, because they're found on Earth. The plasma state is a high energy state. We don't really talk about that in the 6th grade. And in order to go from one state to another, you need to have to add energy or take energy away, and that's usually in the form of heat to go from one state to another one. So even though everything is made up of matter, the reason that all matter doesn't look the same is because the building blocks, the atoms and the elements that make up matter are not the same. So matter is anything that has mass and takes up space, like air, water, dirt, sugar, salt, oxygen, gold, basically anything, okay? And it doesn't matter if you can see it or not. We talked about gases like carbon dioxide in class. You know, one way to prove that a gas is matter is to prove that it takes up space and that it has mass. And if you remember, what I did is I took an empty balloon and put it on the scale, measured the mass, then I blew into it, and you could see that the gas that was coming out of my lungs, the carbon dioxide, was taking up space because the balloon got bigger. And then I tied it and I put it on the balance again and measured the mass, and the mass had increased. It only increased by a few tenths of a gram, but it did show that the air or the carbon dioxide gas had mass. So even if the object is very small and has very little mass and takes up very little space, it's still matter. So mass is just a measure of the amount of matter in an object. This just can be measured on triple beam balance or another type of scale. It tells you how much stuff is in the object. And the unit we use in the science lab, the metric unit for measurement, is grams, and that's a lowercase c is used to lowercase g is used to indicate grams. Volume is the amount of space that an object takes up, and for an object with a regular shape like a block or a cube, you can simply just multiply length times width times height to find the volume. For liquids, you can measure their volume using a graduated cylinder. And also for irregularly shaped solids, you put them in a graduated cylinder and see how much water they displace and find the volume that way. The unit for measurement for solids is centimeters cubed, because if you go length times width times height and you multiply centimeters times centimeters times centimeters, you get centimeters cubed. For liquids, we use milliliters. So 1 milliliter is 1/1000th of a liter. Okay, so all matter is made up of elements. An element is just a pure substance that can't be broken down into something smaller. And we can't change one element into another element either. We talked a little bit too about the fact that matter can't be created or destroyed. So if you put 5 grams of salt into 50 grams of water, you're going to end up with 55 grams of salt water. because even though the salt dissolves, you can't see it anymore, it doesn't disappear, it is still there. So when you combine things, or when you have a chemical reaction, even though it might appear that something has disappeared or the mass has gone away, in a closed system, if you could collect all the gas and everything that was produced, it would be the same mass before and after. Each element has unique properties. We talked mostly about physical properties in our class. It also has chemical properties. So the properties or characteristics can describe how it looks, how hard it is, what's the color. Density is a property. Does it conduct electricity? Is it magnetic? How does it react with other elements? These are all properties that can help describe a substance. And we talked about the fact that atoms make up elements. Atoms are the smallest part of an element that has all the properties of that element. For example, one atom of gold would have the same properties as a bar of gold. Doesn't matter. As long gold is gold is gold, no matter how much of it that you have. Just really quickly, just to have a general understanding, the atom is made up of protons, neutrons, and electrons. The protons and neutrons are found in the nucleus, the center part of the atom. We used the word nucleus before when we were talking about cells. This is a slightly different meaning, but it is the dense center of the atom, and that's where the protons and neutrons are found. Electrons move around outside the nucleus. That's just generally what an atom looks like. We aren't going to go into it, but just so you have a general understanding. Don't get too worried about that. So when we have matter, we have to, figure out ways to measure it, to quantify it, to come up with, a determination of, how much mass is there, how much volume is there, and things like that. So to measure the mass, we worked in the classroom with a triple beam balance. It's just one of the ways that you can measure. You can use digital scales and digital balances as well. But one of the things we learned how to do was to use a triple beam balance. And like it shows in this picture, you put an object on the pan and then you move those riders or sliders along until the pointer points to 0. And when it does that, you add up the values of those riders. You add up how many hundreds of grams, how many tens, and how many ones to determine the mass of the object. Because basically when you're using a triple beam balance, you add up all these things, because the reason it's balanced here, the reason it's at 0, is because the total mass of all of these riders here is equal to the mass of whatever that you put on the pan. So by adding that up, you're determining the mass of the object. And remember, always report the tenths. Even if it's 0.0, report that, so I know that you looked and saw that was 0. For example, the mass of this object, if we had put an object on the pan and we had moved the riders, and the pointer was going to 0, we would add all this up. So this is at 500, so 500 plus 40 plus, and if you look down here, this is 2.4. Okay, so 500 plus 40 plus 2.4 will give you a total of 542.4 grams. All right, now here's where you need to have a paper and pencil or pen. I want you to pause the video here for a minute and figure out on your own what the answers are here, what the masses of these 3 objects are, because when we go to the next slide, the answers will be there. So I want you to pause the video and figure it out on your own. All right, so here are the answers. So for this one, we have 200 plus 90. And if you look over here, this is 0.1.2. So 200 plus 90 plus 0.2 gives you a total of 290.2 grams. So for this one, it's 500 plus 30 plus 6.8. Okay, so 536.8. And for this one, it's 100. There's no tens, okay? So it's 100, and then here it's 5.6. So it's 100 plus 5.6 gives you a total of 105.6 grams. Now going over measuring volume, and the reason I'm talking about measuring mass and volume is because in order to determine density, which is coming up in a minute, You need to know mass and volume. So if the mass and the volume aren't given to you, you have to know how to figure those out. So volume is just talking about the amount of space that an object takes up. And in the metric system, the unit we use for volume is liters, which sometimes you'll see with a capital L, sometimes you'll see with a lowercase l. 1,000 milliliters is equal to 1 liter. And 1 milliliter of liquid is equivalent to 1 centimeter cubed of solid. So those are equivalent measurements. They are considered to be equal. The method or the way of finding the volume of an object depends on a couple of factors. If the object is a liquid or a solid, okay, if it's a liquid, you just put it in a graduated cylinder. If it's a solid, there's two different ways you can get the volume. You have to consider the shape. Is it a regular shape that you could measure the sides and figure out volume that way? Or is it oddly or irregularly shaped? And if it's an odd or irregular shape, we have to use the displacement method, putting it in water, just like Archimedes did, to determine if the crown that the king had made was real gold or not. So remember, because when you put something in water, the amount of water that it displaces or pushes out of the way is equal to the volume of the object. When you're reading a graduated cylinder, when you put a liquid in a graduated cylinder, you need to be careful. And when you take your measurement, you read here at the bottom of this curve, which is the meniscus. Now, when we were looking in the lab, the meniscus most of the time is not this dramatic. But what you want to do is make sure you look at the bottom edge of the liquid and read there. Make sure before you read the cylinder that you know what each of these little graduations or these little marks represent. That's why it's called the graduated cylinder, because it has all of those little marks on it. In this example here, each of these little lines represents 1 milliliter, and we know that because if we count on, we know this is 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay? If you had first guessed and said that each of these lines represented 2 milliliters, if you counted on or skip counted like you did in elementary school and said if this is 10, 12, 14, 16, 18, 20, you would know right away that that's not right, because this isn't 20. 20 is up here. So you need to be very careful and make sure you know what the lines represent before you determine the volume. So again, in this example, each of the little lines is 1 milliliter. So the volume of this liquid would be 10, 11, 12, 13, 14, because if we read across right here, the bottom of the meniscus is at 14 milliliters. When we're measuring a solid, like this cube, and this is the example I showed in class, you just go length times width times height. It doesn't matter to me which side you're saying is length or width or height. It doesn't matter. You just multiply the three numbers together. 10 times 8 times 9 gives you 720. And then it's centimeters cubed, because centimeters times centimeters times centimeters is centimeters cubed. I'm sure you did a little bit of that in math when you're figuring out volume, but in math you might have used inches or feet. It's just a different unit of measurement. Centimeters, it works the same as if you used inches or feet to figure out volume. When we're measuring an oddly shaped solid, we can use the displacement method. Again, this is what Archimedes discovered when he sat down in his full bathtub. The water splashed out. The amount of water that splashed out was equal to the volume, how much of his body was under the water. So when you displace something, you're moving it out of the way. So when you put something in the water, like this rock, it displaces or moves the water out of the way. It pushes the water up in the graduated cylinder, and the amount that it pushes the water up is equal to the volume of that object. So by measuring the difference, so taking the volume of the water with the object in it, and we subtract the volume of just the water, that tells us the difference between these two. The only difference between these two cylinders is that we put this object in it. So the difference in the level of water is equal to the volume of the object. So at the end here, we've got 260 milliliters. We subtract the starting of 200. That means this object, this what looks like a rock, is 60 milliliters. And again, this is just another little example. Again, you got to pay attention to what the little increments here mean. here, if this is 4, 4.2, 4.4, 4.6, 4.8. So before, the volume of the water before was 4.8 milliliters. After we put this little dinosaur toy in, it's 5.2, 5.4, 5.6. So 5.6 milliliters minus 4.8 milliliters gives you a volume of 0.8 milliliters. Now I should have made the correction on here. 0.8 milliliters is the volume of the water displaced, but I should convert that to 0.8 centimeters cubed because we're talking about the volume of the dinosaur, which is a solid. So 0.8 milliliters of water was pushed out of the way, but the volume of this plastic dinosaur, which is a solid, should be reported as 0.8 centimeters cubed. So here's a question. This is a kind of a joke that gets asked a lot. Which one do you think would have the greater mass? A kilogram of feathers or a kilogram of rocks? And which one has the greater volume? And why do you think so? So think about that for a second before we go to the next slide. Both a kilogram of feathers and a kilogram of rocks would have the exact same mass. Sometimes I think that's been told, like, you know, which it weighs more, a ton of bricks or a ton of feathers. They both weigh the same. So a kilogram of feathers and a kilogram of rocks have the exact same mass. The mass is a kilogram. It's the measure of the amount of matter there is for each. But if we looked at a kilogram of feathers, it would have a much larger volume. You would have to have a big pile of feathers. It would take up a lot more space than a kilogram of rocks because the rocks are much more dense. The fact there's less mass per unit volume, which is what density is, for the feathers. So in order to get the same amount of mass, we'd need a really big pile of feathers versus a small pile of rocks. And that's what this image is kind of showing you here. Density is defined as mass per unit volume. It tells you how tightly packed the molecules are in an object. It's basically a ratio of the amount of matter within a certain volume. So if we look at these two examples, and these represent molecules that are kind of crammed into this box shape, this volume. If you look, this example on the left, the density of this one is much more than the density over here. We can see all of these empty spaces. There's empty spaces between these molecules, and here it's very tightly packed. So in the same amount of space, in the same volume, we have much more matter than in this example. So this is more tightly packed. There's more matter in that same space, so this would be more dense. Density is the reason why things sink or float. If something is more dense than a liquid, it will sink. If it is less dense, it will float. Ice floats on top of the water because when ice freezes, it becomes less dense than the water. So it floats on top. So if something is more dense than the liquid, if we took a pebble and put it in the water, it would sink to the bottom. If it is less dense, it will float. This is true for all liquids and solids, and it's why you can create density columns like this. And I made one in class earlier this year when we were talking about the density of the different layers of the earth. When you pour different liquids into a column and then you can add solids in there, they will settle down to whatever level they are depending upon their density. And it creates these layers, and the layers with the greatest density are at the bottom. Things that are more dense will sink to the bottom, and things that are least dense will be here on top. All the solids won't just sink to the bottom. It will depend on their density. Because here we got a popcorn kernel, this is a die, one individual dice, a cherry tomato, some beads, a soda cap, a ping pong ball. So just because it's a solid does not mean it's going to sink. And different liquids will float on top of other liquids, and some liquids will sink to the bottom. Again, it all depends on density. The more tightly packed the molecules of that substance are, the more dense it is, it will sink. The less dense, it will float. So how do you find the density? To find the density, you need to know the mass, and you need to know the volume, and then you need to do some math. So you would find the mass of the object using a triple beam balance or some other kind of scale. You would find the volume of the object. Again, you would find the volume a couple different ways. You could either go length times width times height, or you could find the volume of the liquid by putting it in a cylinder, or you could find the volume of an object by putting it in the liquid and finding the difference. Whatever way you find the volume, you get the volume, and then you divide. Density is equal to mass divided by volume. So when you type that into your calculator, you do it exactly the way you say it as a sentence. You type in the number that you found for your mass, you hit the divide by symbol, and then you type in the number for the volume. It can also be represented this way: D equals M over V, M divided by V, mass over volume, or density is equal to mass divided by volume. Those are all different ways to show the same thing. Units for density are going to be grams over centimeters cubed, because grams is the unit for mass. Centimeters cubed would be for the unit of volume for a liquid. So the reason this unit of measurement, and this trips a lot of people up, it has two parts because it represents mass and volume, mass per unit volume. You divide the mass by the volume. So you've got grams over centimeters cubed for solids, or grams per milliliter, grams over milliliters for liquids. We've seen this image here, density equals mass over volume. It's just this kind of triangle that's used a lot of times in science when you have three different variables. And it just lets you know that as long as you have 2 out of the 3, you can solve for the third. So we're not going to worry about that. But basically, the way this triangle works is if you put your hand over the D here, you would see that mass would be over volume, mass divided by volume. If you were trying to figure out the mass of something, if you put your finger over the M, you would know that you would have to, because these are next to each other, you would have to multiply density times volume to find the mass. And to find volume, it would be mass over density. But we're only worried about density is equal to mass over volume. So to find density, here you're going to have your paper and pencil ready again, because you're going to do a little practice problem. So to find density, you need to know the mass of the object, the volume of the object, and then just divide. Density is mass divided by volume. So if the mass of an object is 35 grams and it takes up 7 centimeters cubed of space, calculate its density. So take a minute on your paper to write down, to set up the problem and figure it out. Write down the formula that you're using, plug your numbers into the formula, then double check your calculations and make sure you add units to your measurement, okay? And pause the video right here, because I'm going to show you the answer on the next slide. So again, if you need to set up your density problem like this, you're given these things. You're given the mass is 35 grams, the volume is 7 centimeters cubed, the formula for figuring it out is density is mass over volume. Our unknown, what are you trying to solve for? This is what you're trying to figure out. What's the density? So the solution is density is equal to 35 grams divided by 7 centimeters cubed. You type that into your calculator and you should get an answer. 35 divided by 7 is 5. And then our unit of measurement, grams per centimeter cubed. That's your 5 grams per centimeter cubed. That's your final answer. The number and the unit of measurement are both necessary for your answer. So density is a physical property of a substance. It doesn't change if the amount of the substance changes. So it doesn't matter if you have a little piece or a big piece, or a super huge piece or a teeny tiny piece. Whatever, if it's a pure substance, the density will be the same no matter what size sample that you have. So in our density lab, you were asked to determine the density of water. Now, some people struggled with this and their answers were a little all over the place, so I'm just going over what you should have gotten, even if you didn't get this, and we're going to be talking about this in class more too. The mass of your water, the first time you did it with a graduated cylinder, you measured an empty graduated cylinder, you added 50 milliliters of water, you put the cylinder back on, found the mass, and then you had to take the difference between the cylinder with the water minus the empty cylinder to find the mass of just the water. So the mass of just the water should have been, because you had 50 milliliters of water, your mass should have been 50 grams. 50 grams of water divided by 50 milliliters gives you a density of 1.0 grams per milliliter. Then you had to do the same thing, only this time get the mass of a plastic cup. Then put 100 milliliters of water in it and find out the mass of just the 100 milliliters of water. You should have gotten approximately 100 grams for the mass for the 100 milliliters of water. 100 grams divided by 100 mils, which is the volume that you read on your cylinder. Again, 1.0 grams per milliliter. So you should see right here, and these were a couple of the questions. The question was, does the density change if the mass changes? No. Here we have 50 grams, we have 100 grams. It doesn't matter that we had twice as much of the material in the second trial as the first one. The density was still the same. Doesn't matter if the volume, the space it takes up is different. No. Density does not matter. It does not matter if the mass and the volumes are different. The density of pure water is always going to be 1 gram per milliliter. It does not matter if you have 1 drop or 100 liters. It's going to be the same density, 1. Finding the density of an unknown substance can help you determine what that substance is, because you can compare the information to tables of known values. It can help you figure out what you're looking at. Finding the density of an unknown substance can also tell you if that substance is going to sink or float in water. If you're not sure, you can calculate the density of it. Density of water is always 1, like we just talked about in the previous slide. If the density of the unknown substance is more than 1 gram per milliliter, the substance is going to sink in water. Or more than 1 gram per centimeter cubed, if you're talking about a solid, it's going to sink. If the density of the unknown substance is less than 1 gram per milliliter or less than 1 gram per centimeter cubed, the substance will float on top of the water. If the density of the substance is exactly 1, it's going to be like right there in the middle of the water. It's going to look like it's suspended in there. If you know the density of a variety of substances, you can figure out how they would form layers if placed in a graduated cylinder to make a density column, like I showed you a few slides ago with all those different liquids and solids. So they will just make layers with the most dense layer on the bottom and the least dense layer on top, and it will just go in order of density. The final section of this unit is energy and chemical reactions. A chemical reaction occurs when 2 or more substances combine to form a new substance. The compounds that are formed, or whatever is made, occur when 2 or more atoms of different elements are joined together during a chemical reaction. There are 4 main pieces of evidence of a chemical reaction that we look for. Is a gas formed? Do you see bubbles? That tells you that a chemical reaction is happening. Is there an unexpected color change? Does something change from pink to blue or pink to green? If you add food coloring to water, that's not an unexpected color change. That is expected. If it's unexpected, that's when you know a chemical reaction is happening. Is there a change in temperature? Does it get hotter or colder? That's evidence that a chemical reaction is happening. And if a precipitate or a solid is formed, a new solid is formed, that's evidence. That these new substances that are made have properties that are different from the original substances or elements that make them up. So these are some examples. A change in color, bleaching your hair, it changes its color. There's a chemical reaction that takes place that removes the color from the hair. A change in temperature, burning wood produces heat. We did the cold packs in class. They feel colder. That's a chemical reaction taking place. Production of a gas. If you use Alka-Seltzer tablets and you put them in water, it produces gas bubbles. That's a chemical reaction. And this shows production of a solid. Adding an acid to milk produces solid curds of cottage cheese. These are all chemical reactions that are taking place. So when you have a chemical reaction, in general what's happening is you start off with some reactants. This is what you start off with, your ingredients, whatever you're mixing together to see if something's going to happen. And what you end up with is your products. And if a chemical reaction has taken place, the products are going to be different than the reactants. You will have made at least 1 or more new things. The products are what you end up with. It's what is produced. And so there's 2 kinds of reactions. Endothermic reactions, they need to absorb heat. They need to take heat in order for the reaction to take place. The prefix endo means inside, so the heat is going in to drive the reaction forward. The products are often colder than the reactants. For example, when we did the cold pack in class, when you kind of crush the pack and start the reaction, you activate it, the pack starts to feel colder. It's an endothermic reaction. The heat is going inside to make that reaction take place. In the lab, we also mixed lemon juice with baking soda, and when you recorded the temperature, you noticed that the temperature went down. Another way to know if something is an endothermic reaction is if the reaction won't take place without adding heat. For example, cooking an egg or baking a cake. Those are endothermic reactions. If you just leave the egg in the pan without turning on the stove, or you leave the batter in the bowl and never put it in the oven, those reactions are never going to take place. You're never going to cook that egg. You're never going to get a cake. You need to add that heat energy. That energy needs to be absorbed in order for the reaction to take place. Exothermic reactions are reactions that give off heat as the reaction takes place. Exo means outside. The heat comes out. And sometimes it can come out explosively, like when you have an explosion of fireworks or dynamite. In exothermic reactions, the products are going to be hotter than the reactants. So what you end up with is hotter, sometimes warmer, sometimes a lot hotter than what you started off with. Some reactions give off a little heat, like when we combined beef liver and hydrogen peroxide in the lab, it was a little warm. Some reactions can give off a lot of heat, like dynamite exploding, fireworks going off. That's a dangerous amount of heat that can be destructive. So again, just to visualize exothermic versus endothermic, if you figure, like, think of arrows. Exo means exit. Heat is exiting. Heat is coming out. It feels warmer. Endothermic, the heat has to go in order for the reaction to take place. So sometimes that feels colder, like when we did the cold packs. But sometimes, another example of endothermic reactions is things where you need to apply heat. You need to put heat in there, like cooking something, to get the reaction to take place. And one way you can tell whether a reaction is exothermic or endothermic, is to just use a thermometer. That's what we did in our lab. So if you measure the temperature of the reactants, what you're starting with, and you measure the temperature of the products, what you end up with, you can know whether it's endothermic or exothermic. If the temperature goes down, it's an endothermic reaction. If the temperature on the thermometer goes up, it's exothermic. So please review this video again. Come to me with any questions that you have, and study for the test.